Hello everyone, today we're talking about eccentricity and parametric equations, last couple of chapters for chapter 9. So it's important to know exactly what we're looking for in a polar equation, and then we can determine the eccentricity, and from there we can determine whether it's a parabola, ellipse, or hyperbola from the given polar equation. So, if we're given this polar equation, the first thing we're going to have to do to identify the conic, we're really only worried about identifying the conic. We're not worried about graphing it, labeling the vertices. We're not worried about that. All we want to do is identify the conic. So, if you go back, in order to identify the conic, we have to have this 1 here in our denominator. So, you'll notice that we have a 3 in our denominator. So I've got to divide my denominator by 3 so that I have a 1. So when I divide that denominator by 3, I get r equals 10 over 1 minus 2/3 sine theta. Okay, so now we can see that I have a 2/3 in front of my sine. That is my eccentricity. So that eccentricity, we just go back and look at the types of eccentricities we have. So if my E, so if this so happens that the eccentricity in front of my sine or cosine is 1, we have a parabola. If the eccentricity in front of my sine and cosine is between 0 and 1, meaning we have a fraction, then we have an ellipse. And if the eccentricity is greater than 1, meaning we have an improper fraction, right? We have a larger number in the numerator than the denominator, then we have a hyperbola. So if we go back and check what we just found, okay, we have an eccentricity between 0 and 1. So that means we have an ellipse. And that's all we're worried about. So it's important to note here, and they will throw questions like this at you. You can't just look straight at the denominator and say, oh, that's a 2, that's greater than 1, it's a hyperbola. You have to make sure this leading number here is a 1 before you determine the eccentricity. After that, it's easy to tell what type of conic we have. Now, they want us to sketch the curve represented by a parametric equation, and then find the rectangular coordinate equation by eliminating the parameters. So, this is just a parametric equation, means we basically have a third variable. But we can go ahead and solve. We can graph it, and then we can actually get it back into rectangular coordinates, or a rectangular equation where we know it looks familiar to us. So in order to graph it first, before going to a rectangular equation, we're going to go ahead and make a table. So our table is going to have t, and then x, and y, depending on what t value we plug in. So I like to start with 0, 1, 2, and we'll see if we need to add more t values after that, or we'll see if we can see what's kind of happening. So when I plug a 0 in for t, I get a 0 back for x, and I get a 0 back for y. So all I'm doing is plugging 0 in for t. When I plug a 1 in for t, I get a 1 back for x, and a 1 back for y. When I get a 2 in for t, I get a 2 back for x and a 4 back for y. And let's just do a couple negative numbers to see what's happening on the negative side. So if I plug a negative 1 in for t, I get a negative 1 in for x, and I get a positive 2. And if I plug a negative 2 in for t, I get a negative 2 for x and a positive 4 for y. Meaning, if I go ahead and put a grid in here, let's see, we want to go up to 9. So if I went one more, just so that we can fill out the graph, if I went up to 3, we'd realize this is 3 and this is 9, the y is just squaring our t. So if I go ahead and plot these points, I'm just worried about plotting the xy points. Right? The t is my parameter here. It's the third variable. So I'm just going to worry about plotting my xy points. So we get 0, 0, we get 1, 1, we get 2, 4, and we get 3, 9, and we get negative 1, 1, negative 2, 4, and then if you were to plug negative 3 in, you'd get negative 3, 9, so we can kind of see the graph that's happening here. Okay, so it looks like we probably know that graph just by looking at it. Well, let's go ahead now and eliminate the parameter. So let's go and get that straight into rectangular coordinates. So they gave me x was equal to t and y was equal to t squared. Well, we want to try to solve x for t. Well, we already have t equal to x, so I can plug that in over here. So instead of t, I'm going to plug an x in, and we get the equation y equals x squared, which if you graph y equals x squared, you are going to get this graph. So we first graphed using the parametric equations. We first used those to go ahead and plot some points, and then we eliminated the parameter. We got rid of that third variable by solving for t. It was convenient. It was already solved for t, and then plugging it into the second equation. So since that one was so simple, I have one that's a little more difficult. So again, we're sketching and then turning it into rectangular coordinates. So we're always going to start with our chart, where we have our t, our x, and our y. And let's just start with 0, 1, 2, see what happens there. So I plug a 0 in for t into my x equation. I get 0 squared times 5, 0. And if I plug a 0 into my y equation, I get 0 squared minus 1, so I get a negative 1. If I plug a 1 in, I get a 5 for my x, and I get a 0 for my y. If I plug a 2 in, I get 4 times 5, I get 20, and I get 4 minus 1 is 3. Okay, so we can see as I make my t a little bit larger, it's just going to push it out further to the right. So let's see what happens if I make my t negative. Let's see what happens. So if I plug a negative 1 into my x, I still get 5. And if I plug a negative 1 in for my y, I still get 0. And if I plug a negative 2 in, I still get 20. And I still get 3. So we can see that by going negative, that's really not changing any values. We're still going to get values that start at x equals 0 and go to the right. So if I go ahead and put my graph in, let's do this one. And we'll get it down here so we can see it better. And we'll go ahead and plot our points. First is x is 0, y equals negative 1. And I'll do the y scale stay the same, but I'm going to change the x scale to be 4 each. So I'm going to pretend I'm going to pretend this is 5, 10, 20, or 15. Double 10. 15, 20, 25. I'm going to pretend the x scale is going out by 5. So I plug the next point in, 5, 0. The next point is 20, and then 3. And maybe I don't want to spread it out. I will act like all of these, negative 5, negative 10, and 5. So my first point here, that's close enough. 0, negative 1, and then 23. Okay, so we can see that the graph is doing something like this. Okay, so I've plotted my parametric equations. There's no value I can plug in. Just to give you an example, I did 1/2 just to show you that the fractions aren't changing much. That gives us 1.25 and negative 0.75. So that puts it, 1.25, or puts us right about there, which falls on the line, but we're never going to get anything on the left-hand side of the y-axis. We're never going to be able to get a negative value for x, which makes sense because we have a squared term. And just a number times a squared term. So the square is never going to be negative, so if we multiply a positive number times a number that's always positive, obviously we're always going to have positive numbers. So now let's go ahead and eliminate the parameters. So we've graphed the parametric equations. Now we're going to eliminate it so it's just rectangular form. So they gave us that x equal 5t squared, and they gave us that y equals t squared minus 1. So to eliminate the parameter, I first have to solve for t. So I'm going to solve the x equation for t. So first divide by 5. So I get x over 5 equals t squared. And then I take the square root, giving me t is equal to square root of x over 5. Cool. Now that I know what t is equal to, I can take that, substitute it into my y equation. And so I get the square root of x over 5, all squared. And if I simplify, the square and the square root are going to cancel. So I just get the line y equals x over 5 minus 1. And I didn't do a very good job of drawing the line. But actually, if you graph those points a little bit neater, and you compare it to the graph y equals x over 5 minus 1, you're going to see that the points actually line up. And that's more what we're worried about, that the points line up, not necessarily how accurate your graph is drawn. Only thing about this equation is, this equation here, we could get negative x values. Right? We could plug a negative x value in and get a y value back. So we have to put a little limitation on this equation and say that y is equal to x over 5 minus 1, but x must be greater than or equal to 0. Right? If we want that equation to look exactly like the parametric equation we drew, we can't have any x values that are less than 0. So if you were to plot this, if you were to graph this, you'd see we get the same points, and the only restraint being x can't be less than 0. X can be equal to 0, since we had x equal to 0 in our chart, but we're never going to be able to make it negative. So go ahead, try the example problems that accompany this in the PowerPoint. Answers are again at the end, so you can check your answers, and we'll talk about it in class tomorrow.